Okay, and away we go. So, before I turned on the video, we were just kind of chatting about Sir Isaac Newton and Gottfried Leibniz. I might put there's some really good videos that on YouTube where they I think there's one especially where they do a little animations and kind of the feud between Leibniz and Newton. Not actually, really, you could call it the feud between Sir Isaac Newton and mathematicians in the rest of the world. And it's pretty cool. I'll see if I can find a good one and put it on a good YouTube video and put it on my blog so that you guys can see it. It's really interesting stuff. So that's the first thing some people might have noticed. It's like, hey, Lagrange and Leibniz. I thought calculus was all about Newton and Leibniz because that's the story. But Lagrange is the notation that we use the most. So there's he saying that we write it down as the derivative is just f primed of x. And that's what we've been doing so far. But Leibniz notation is really common too. And when Mr. Lacko put the sheet together, he accidentally cut and pasted this in twice. So you can see he has the same thing here twice. So I just like to think that it's so important that he said it twice. You weren't listening the first time, so he said it twice. And if you say y is equal to the function of x, when you're hitting a derivative, you say the derivative of function y with respect to the variable x. So that's actually, if you want to add that maybe as a little, how do you say what you're looking at there? Because that's part of learning notation in math, right? It's all well and good to look at a bunch of symbols on the page, but if you have to say it out loud, how do you say it? Most people would read this as the derivative. Oops, oh, hang on, I just accidentally turned on my eraser. Let me start that again. The derivative of y with respect to x. So that's basically what that's saying. Okay? And of course we know, and we've now learned that the derivative of a function will always be the next degree down from the function you start with. A squared, a quadratic, will end up being a linear. A cubic will end up being a quadratic, etc., etc. And if you're wondering, the letter D here, of course, can stand for derivative, but that's actually, I'm saying that, but that's actually not what Leibniz meant. The letter D got used because the letter D has its analogy in the Greek alphabet as delta. And oh, wait a minute, delta y over delta x, does that look familiar? Slope, yeah. So that's why he chose the notation that he did, because it kind of links back to what a derivative really is, the slope of a tangent to the curve. Okay, so that's the notation. And again, Leibniz's notation, because it links right to slope, is the one that they use the most in the sciences, because it has that advantage of always getting you to think, oh yeah, velocity is just the derivative, velocity is just the derivative of position, meaning that it's the change in position over the change in time. Okay, and there we go, differentiation. And these, of course, remember that you can always express a function as just a second variable, y equals something x, or you can write f of x, and using Leibniz's notation, those two things look pretty much the same. So you can say that the derivative with respect to x. So if you don't have a second variable, you can just write it like this. These things basically say the same thing. Okay? Now, we've done a few things where it's like, for example, we've done things like, what's f primed of 3? In other words, what's the slope when x equals 3? How do you do something like that in Leibniz notation? You'd write it like this, where the 3 would just be where the a number is. So that's the same thing as saying f primed of a. Okay, so I don't really want to spend a lot of time on this handout. This handout's just kind of there as something for you to look back on if you ever are getting lost in the notation as you're looking at your homework. You can look back to this sheet and remind yourself what it's saying. Today, we're going to actually start with simplifying the rules of derivation and differentiation. And I have good news for you. Once you learn how to do it this way, you won't be using first principles almost ever again, except when we want to make sure we can test you on your ability to use first principles. So here comes the basic derivative rules. First one is called the power rule. if a function of x is equal to x to some power, then the derivative of that function follows this little formula here. In Leibniz notation, you'd say if I have, I'll just use y, if y equals x to some n, then the derivative of function y with respect to x is equal to, and it's the same formula, n times x to the n minus 1. So instead of breaking out that great big, the limit as h approaches 0 of f of h, x plus h, yada, 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 I can just look at this and follow the formula. F primed of x is equal to, look at the way the formula works, this exponent becomes the coefficient, and then the exponent becomes 1 less, which is, again, that little pattern that we've noticed, that when we do the derivatives, we always end up a degree smaller than the thing we started with. Let's do this one in Leibniz notation. If y is equal to x to the power of 100, the derivative of y with respect to x is 100 x to the power of 99. And thank goodness we have this rule. Could you imagine doing question B by first principles? We'd have to expand a x plus h to the power of 100. Better break out the Pascal triangle there and figure out what the coefficients are on that thing when you expand it. All right. So if y equals 1 over x cubed, what do I do with that? Well, for this one, I'm going to simplify it a bit first. I'm going to change this to y is equal to x to the negative 3. Everybody remember how exponents work when they are reciprocals? So that means that the derivative of y with respect to x is negative 3x. Now careful, if you subtract 1 from negative 3, you now have negative 4. And you could leave the answer like that, or most textbooks don't like answers that leave negatives on exponents. So you might want to change that back to negative 3 over x to the 4. And make sure it makes sense to you why the negative 3 stays on top. Okay? Don't bother writing this down. But I see this mistake so often it drives me crazy. I see students who look at that and they'll go, oh yeah, that's a reciprocal, I know that. This is the same mistake that if you're doing this and I say, okay, x is 2. Well, if x is 2, is this 2 times 8, or is this 4 to the power of 3? Right? Well, most of you go, oh, well, it's 2 times 8, right? You use exponent first, then multiply by the coefficient. Basic bedmass. E counts before m, right? Exponent, then multiply. Most people don't mess that up. Most people know it's this and not that. So then why are they doing this? It's the same mistake, right? This 3 is not being taken to this power. It's a coefficient. So make sure that makes sense to you. Every year, people make this mistake over and over again. It's beneath you. All right. Any questions so far? This is saying the same thing as all the others. What's the derivative with respect to x of x to the power of 6? Notice I don't even need a second variable. I don't even need to be told it's f of x or that it's y equals. It's just an expression. It's not an equation, but I need to find the derivative of that expression. So no problem. The derivative with respect to x of x to the power of 6 is 6x to the 5. What do I do with the last one? Once again, I have to somehow come up with an exponent here so that I can use my exponent or my power rule. Oh, oops, sorry. What exponent goes on the square root of x? The square root of x is the same as saying x to the power of 1/2. So that means the derivative would be 1/2 x. Now careful here. What's a half minus 1? Negative a half. Okay, now, that's a perfectly good answer, but again, most textbooks don't like having negative exponents in the final answer. So how do we fix that? Well, that would be 1 over 2x to the 1/2. Does the logic of that make sense to you? And some places might not even leave that as the final answer, because some places would say, oh, we don't want rational exponents. Can you put that back into radical form? So you might have this then. And then there might even be textbooks that go, oh yeah, but we don't want radicals in our denominator either. Fine, I can fix that too. What did I do between here and here? Right, I rationalized the denominator. I multiplied top and bottom by root x. So all of these things say the same thing. See how important notation gets? Right, they all say the same thing, right? If you were doing your homework and you got to here and the final answer in the textbook was at the other end, would you recognize that you had the right answer? Some people are nodding yes, that's good. Some people are going no. Then you got to brush up on this, right? The ability to switch from rational exponents to radicals or from negative exponents to rational expressions, that should be very fluid for you. That should be a skill that's comfortable because it's going to happen a lot. So that's the first rule. That is the rule we call the power rule. The constant rule is really easy. If the function is just some constant, the derivative of that constant is 0. And that makes sense, right? A constant is a horizontal line. What's the slope of a horizontal line? Nothing. It doesn't have a slope. It's 0. So in Leibniz notation, I'd write if y equals some constant c, then dy by dx is equal to 0. And another way you could kind of show that that's true, I'll say think y is equal to c is the same thing as saying y is equal to c times x to the 0, right? So if you want to use your power rule on that, dy by dx would equal 0 times c times x to the 0 minus 1. Well, it doesn't really matter what x to the 0 minus 1 is, because if you're timesing by 0, the whole thing is 0. So these ones are really easy. I don't know why we gave you so much room for them. F of x equals 7? Great. F primed of x is nothing. Y equals negative 4? Great. dy by dx is equal to 0. The derivative of a constant is 0, which makes sense, because the slope of a horizontal line is 0. Okay, that rule is not very interesting. The constant multiple rule basically says that if you multiply a coefficient by a function, the derivative of that function doesn't really change the fact that the coefficient's there. So for example, f of x is equal to 4x cubed, then f primed of x is equal to 4 times 3x squared. Get it? That 4 doesn't go anywhere. Oh, but now it has a 3 it can combine with. So I would simplify that to 12x squared. Let's do this one in Leibniz notation. Y is equal to negative 3x to the 5. Then the derivative of y with respect to x is equal to negative 3 times 5 x to the 4, which I can simplify to negative 15x to the 4. Once you get kind of used to what you're doing here, I really don't need to see this step. I don't mind if you just jump right to the answer. Okay, let's try a couple more of those. Y is equal to 6x to the exponent 8/3. All right, so let's see what we can do with that. So y primed. Let's do that instead of Leibniz notation. Let's use Lagrange's notation, but with a y instead of an f of x. Y primed is equal to 8/3 times. Oh, I guess I should put the 6 first, just to kind of keep consistent. Whoops. Just to keep consistent with the way I was doing the other ones. Doesn't matter, right? You can multiply two things in any order you want. So 6 times 8/3 times x to the, okay, think about this. What is 8/3 minus 1? 5/3, very good. So also I noticed that 3 goes into 6 twice. So y primed is actually going to equal 16x to the 5/3. And once again, I'm happy with that as an answer. If the question didn't tell you what format the answer should be, you could just leave it there. That's a perfectly good answer. But what if it did not want a fractional exponent? What if it wanted it in radical form? We've had this conversation, I think, right? X to the power of, say, 5/3, well, yeah, 5/3, any fractional exponent. That's the same thing as saying x to the 5 to the power of 1/3, or it's the same as saying x to the 1/3 to the power of 5. Do you get why that's true? It's because remember when you take the power of a power, what do you do with those two numbers? You multiply those exponents, right? So notice it doesn't matter what order you multiply two numbers. So x to the power of 5/3, if I want to turn that into a radical, I want it as simple as I can make it, right? So I think actually this way might be the easier way to do it, because I can write this as the cube root of x to the 5. And then again, I could leave it like that. That's a perfectly good answer. So this could be 16 and then cube root of x to the 5. Or I could now simplify that radical a little, because think about it. X to the 5 has a perfect cube in it, right? Going back over here. The cube root of x to the 5 is like saying the cube root of x cubed times x squared. And the cube root of x cubed is just x. So some textbooks might think that's the simpler answer. So that would equal 16x cube root x squared. All of these things are the same number. Feel free to feel free to go onto Desmos and graph y equals this thing, y equals that thing, and y equals that thing. All three things will be the same line. Now that I think about it, I don't even know how you'd put this into Desmos. Can you do that? Cube root of x to the 5 on Desmos? You'd have to try it. I don't know. I think you can. All right, so moving along. This one, again, I'll just use y. I'll do Leibniz this time. dy by dx is equal to 3 times negative 1/3. I'll use brackets so I don't accidentally think that's a subtract. 3 times negative 1/3 times x to the negative 1/3 minus 1. All right, what's that going to look like? Well, the 3's cancel, and that's going to be x. Negative 1/3 minus 1 is negative 4/3, right? Because remember, 1 is 3/3, right? Now, once again, I don't want negative exponents in my answer, so I could write that as negative 1 over x to the negative 4/3. And every once in a while, I'll get a student who they'll do a question like this, and all of a sudden, the negative's gone. Oh, wait a minute, sorry. This negative should be gone. My bad. 4/3. There, I used the negative to make it a reciprocal. It's gone. But sometimes I'll have students who they'll make this negative go away as well. They'll just cancel that out or something. Well, you can't cancel it out. They'll say, yeah, there's a negative times a negative. They cancel. No. This negative isn't really a negative value, right? It's just telling you have a reciprocal function. Okay, so that's a perfectly good answer, right? Or again, I could change that into radical form. Negative 1 over the cube root of x to the 4. That's a perfectly good answer. Or I could leave it as negative 1 over x cube root x. And do you see why all three of these are the same thing? Oh, and then of course there's people who go, yeah, but I don't want a radical in the denominator. I'll leave that up to you. You can try to figure out how to make that rationalized if you like. Okay? All right. Let's try this one now. H primed of x would be negative 2/3 is going to stay there. The 4 is going to become part of that coefficient, and this is now going to be to the power of 3. So I would leave that as negative 8/3 x cubed. And then finally f, g of x. Let's do this one in Leibniz notation. So how about, if that's g of x, I can say d of function g with respect to x, or actually, I think I'll write it this way. Let's do this one differently. Let's write this one as the derivative with respect to x of function g. Sometimes you'll see it written like that. That's the same thing. Is 3/4 times negative 8 times x to the negative 9, which I would write simplified as negative 6 x to the negative 9. And if I didn't want to have a negative exponent in my answer, it'd be 6 over x to the 9. All right, so that is the constant multiple and the power rules. The sum rule is basically just that if you're adding together different functions, you can, of course, do the derivative of them separately and then add them together. So in Leibniz notation, the derivative with respect to x of function f of x plus function g of x is really basically just the derivative with respect to x of function f plus the derivative with respect to x of function g. And subtract is exactly the same thing, only instead of adding the two functions together, you're subtracting. And it should make sense that those two rules are basically the same, right? Subtraction isn't really a different operation than addition. Aren't they opposites? Well, yeah, but they're also kind of the same because adding a negative is no different than subtracting a positive, right? They are the same operation logically. So these rules should be pretty self-evident once you start doing a couple of examples. So let's take a look. Give you a sec to catch up to me here. What time are we done? We are done at 59. So we got 10 minutes. Okay. Okay, so I'm going to try to get through these last. Oh, there's only 3 more examples. Oh, right, we're stopping at this page, right? Sorry. I thought for a minute we were doing the next rule after that. No, we're not. This is the last rule for the day. Okay. So here we go. 4x cubed minus 6x squared plus 3. What do we do with that? Well, the derivative is, consider these 3 things as 3 separate functions. Right? There's a 4x cubed function, a negative 6x squared function, and a function of 3. So the derivative of 4x cubed, using my power rule, is 12x squared, minus the derivative of 6x squared is 12x. And of course, what's the derivative of a constant again? I'm not even going to bother writing that. There we go. Think about how much work A would have been using the first principles formula. Right? I mean, do you even want to think about that? That would have been, let's see, that would have been the limit as h approaches 0, you don't have to write this down, of f of x plus h. So what would that have been? That would have been 4x plus h cubed minus 6x plus h squared plus 3 minus 4x cubed plus 6x squared minus 3 all over h. Expand that, cancel out those guys. At the end of the day, after all that work, we'd have ended up here. That's a lot less work. Okay, so hopefully we understand that these rules greatly simplify our ability to find derivatives. Let's do this one. So y. So let's do this one as dy by dx. The derivative of y with respect to x is negative 3 times 4, which is negative 12, x cubed. Careful here. Plus 15x to the negative 4, and of course plus 0. Oh, why'd I write plus 0? I don't know. I said it, so I wrote it down. Plus 0. Okay, I'm going to simplify that one because I don't want a negative exponent in my answer. So there. That's the way I would leave that answer. All right, what are we going to do with c? Well, we'll simplify it first. So g of x is, let's expand that. 4x times 2x cubed is 8x to the 4. 4x times negative 2 is negative 8x. 3 times 2x cubed is plus 6x cubed. And 3 times negative 2 is negative 6. Are there any like terms here? No. I remember doing an example like this and somebody said, what? I thought anytime you times 2 binomials, you get a trinomial, because that's the way we learned it in grade 10. No, that's only true if the degree in both the binomials is the same, right? If you have more than one degree of the variable being multiplied together in the 2 different brackets, it won't turn out that it simplifies to a trinomial. And this is one of those cases. That's not going to simplify. So we'll just work from here. G primed of x is 32x cubed minus, now careful with this one, right? That's just going to be 8. Do you get why that's just 8? You want me to write it down? Because think about what happened, right? This 1 that's here became something that multiplied with the negative 8, and then 1 minus 1 is 0, plus 18x squared minus 0. And then let's just tidy all that up. That's 32x cubed. I'll rearrange it in order of descending powers too. There we go. Okay, so you can now do 2.2. I haven't actually updated the blog yet. So my son was on our main computer last night till late working on an exam he had to finish for U of M. So it's like, I'll update the blog tomorrow. I like to always have my blog update done before I start my day. So I'm feeling very discombobulated today. But all right, here we go. Let's see, 2.2. You can do number 1. You can do number 2. You can do number 3. 4 is pretty good. Okay, and then starting at number 5, it says use the definition of a derivative. And that means you have to go back to first principles formula. But we've done enough of that, so we'll skip number 5. So 1 to 4, and 7's a cool question. I like 7. I like 8. So 7 to 9's pretty cool. 10's pretty cool. 11's kind of a drag. 12's kind of cool. So I'm going to go 7 to 10 and then 12. So that'll be the homework for this stuff. And I'll put that up on the blog right away. And if I can find that cute little YouTube video about the war between Leibniz and Newton, I'll put a link to that too. Okay? And then Monday, I think Monday I won't do a new lesson. I'll just, we'll go maybe talk about your quiz a little bit. So you guys will get the quiz back, your last test, I mean. You guys will get your test back Monday. Guys at home, remember, tomorrow counts as a day, guys at home, right? So make sure you don't come to school Monday. Guys at home, right? Tomorrow counts as a day even though you're not here. So you guys get 2 days in a row. And guys at home, you get 2 days at home on teams in a row. You know, it's very confusing. But unless it's a holiday for every school, they can't not count it as a day. That's the deal. Okay. So, enjoy your long weekend. I know there's a couple of you that I'm going to be doing a Teams meeting with your parents or a phone call with your parents, and I'm looking forward to that. Have a great rest of your day. I don't think I have to mark anybody absent, right? Every desk that I had something handed on was full. And I'll do a attendance for the team meeting here.
Thanks, Mr. Fellow.
Have a great weekend. And there we go. Okay. Anybody wants any help with anything, I can be around. Just give me a minute to update my blog. All right. Okay, blog. Oh, oops, forgot to turn off the video.